Okay, we're going to talk about titrations to finish up the chapter. When you look in the back of the lab area, you see all those burettes. They're working on titrations also, so it's set up back there. But it's a laboratory procedure used to determine the molarity of an acid or base. If you know the molarity of one or the other, and you have an unknown solution and you want to know what the concentration is, you can perform a titration and figure out what the molarity would be. And so we're using a base or an acid to neutralize the other. And so in this case, it looks like this is the acid solution down here on the bottom.
So I heard the quiz went well.
Acid down here, you use an indicator, and we'll use phenolphthalein, and that would be clear in an acidic solution, and once it turns to a basic, then it's going to be pink. So it's going to be clear, and then it will automatically turn pink with one drop of a solution. Whoops. So the solution of an accurately known concentration is added gradually to another solution of unknown. So we have an unknown concentration. Quiet. So you have an unknown concentration, and you add a solution that you know the concentration of. And once you get to the point where the reaction is complete, that's called the equivalence point. And we use an indicator, and there's lots of different indicators that change different colors. We use phenolphthalein because it changes color at the correct pH that we want to change color. And we are going to... acidic, it's going to be clear, and then we add until it turns pink. Add base. So the end point of a titration is when the indicator changes color. Not all indicators change color at the same pH. I think your book has a picture of some other indicators, but some go from green to yellow. Some change blue to pink. So there's different color changes that can occur at different pHs. So if you're looking at a solution that is reacted and it gets to equivalence point at something below 7, you probably don't want to use phenolphthalein because that would not give you the correct endpoint. Oops.
Did you skip one?
I don't think I did I?
Come on, Coach, don't skip any. Let's go.
Oops. Oh, it would be 7. The pH would be 7. Oh, shoot. So here's some other indicators. So like thymol blue is red in acid, yellow in a base. And it changes color between 1.2 and 2.8. So that would not be a good indicator for a strong base, strong acid titration, which is why we use phenolphthalein as the one. It goes from colorless to a reddish pink. There. We could also use, it looks like Cresol red would go from yellow to red. That color change is just harder to see, so the phenolphthalein works better. Bromethymol blue would probably actually work too, yellow to blue. So here, you can use cabbage. Did you guys use cabbage solutions in biology to look at pH? You boiled the purple cabbage, and if you boil purple cabbage and you use the water that's left over, you can see what pH it is. It changes color. So here would be an acidic. And as the pH goes up, it turns more yellow. This is just showing where the different color changes occur. So this is what, what's the next slide? No, I don't want that. Okay, so this is called a titration curve. And what is going on is if you have an acidic solution and you're adding base, the pH slowly goes up until you have the equal number of moles and that gets to its equivalence point, and that's right here. So it's that equivalence point is right at this vertical point of the graph. And so what you want to do is pick a indicator that changes color at one of those pHs within the equivalence point. So phenolphthalein is one that would work. And then if you continue adding base, the pH would keep rising. So you're looking for what volume gets you to this equivalence point, that vertical point. So calculating molarity using our titration. I think the steps they give you are kind of confusing. So we're just going to go through how to solve this. Those acid-base titration ones you can cross out. Except for... Okay, cross out on your notes where it says acid-base titration, the strong acid, weak base titration. Cross that out. And then didn't we have something about the indicator? Yeah, so endpoint, not all indicators change color at the same pH. Oh, you can cross out that problem. Yes. Okay, then we're going to go through and solve this problem together, but I'm going to just do it on a blank page. 18.5 milliliters. Hold on, it's thinking. So we need a balanced equation first. What are we going to get as our products? Neutralization reaction. And it said we use 18.5 milliliters of a 0.225 molar solution of sodium hydroxide. And it titrated 10 milliliters of hydrochloric acid. And we want to know what the molarity is. So what we need to figure out is how many moles of sodium hydroxide was reacted. And since it's at the equivalence point, that's where all of the sodium hydroxide has reacted and all of the hydrochloric acid has reacted. So the number of moles, since it's a 1-to-1 ratio, would be equal. And then since we know moles and we know the volume, we can then calculate the molarity. So how would we find the moles of sodium hydroxide? Molarity is equal to moles over liters, right? So do we know the molarity of sodium hydroxide? It's 0.225. What volume in liters do we have? Right. We have to change that to liters. So then how many moles? We multiply those two together and we get the number of moles of sodium hydroxide. What is that? Does someone have their calculator out? What is it? And that is NaOH. Oh, It sounded like 0.085 back here. Now, we are going to figure out how many moles of hydrochloric acid reacted then. If 0.004 moles reacted with sodium hydroxide, we would use our coefficients. In this case, it's a 1-to-1 ratio, so really they're going to be equal, but let's just show that step just so that we know how we got there. Because sometimes your problems are not going to be 1-to-1 ratios. So how many moles of acid? The same, so 0.004 moles of HCl. And to calculate molarity, you would take moles divided by liters. Do we know how many liters of acid we use? 0.01 liters. .416. Right, so this would have been a 616. So there would be our molarity. Questions on that? Yeah. Because it's 10 milliliters, and we need it in liters, so we just change that to liters. Divide by 1,000 to get to liters. So this is one of those things that's a process, not really an equation that I'll be able to give you for that. For the test, I'll give you the equations that are on the board, but not really an equation for this. So let's do another one. Isn't there another one in your notes? Okay, so this one's a little different because we're calculating milliliters. But if we can get to moles of acid and we know the molarity, can't we figure out what the volume would be? I think so. So we have sulfuric acid reacting with, with what was it reacting with? I didn't see. Sodium hydroxide or potassium hydroxide?
Pick up.
Is that my phone?
Yeah.
Someone might be leaving a message. So what are we going to get? Potassium sulfate is K2SO4. So we're going to have to put a 2 here and a 2 here. And we know that this is 2.0 molar. And this is 1.0 molar, and it took 50 milliliters. Yes, SO4 is 2 minus. And we're looking for X milliliters. So we're trying to find how many milliliters that is. So we need to find how many moles of base are reacting. If we know it's 1.0 molar, that's moles per liter. How many liters is this? 0.05 liters, so 0.05 moles of KOH. Let's figure out how many moles of acid was reacted then. We need moles of KOH on the bottom and moles. Right, you'd have a 2 here and a 1 here. Why do we use a 1 and 2? The coefficients from the balanced equation, right? So this is 0.025 moles of H2SO4. So if we knew the volume, we would find the molarity, but we know the molarity is 2.0 molar, and we know the moles is 0.025. So then can we find liters?
Yeah. You divide by 2.
Right, so you take 0.025 divided by 2.
0.0125.
Liters, and it specifically asks for milliliters in the question, so we'll change that to milliliters, so it's 12.5 milliliters. And that would be our answer. Do you get the same answer? And it's just moles per liter as molarity. It's not moles per. Maybe if you make sure all your volumes are in the same unit, it works out. No, I've always changed it to liters.
It's easy to remember because you know it's closer.
Mm-hmm. Okay, and then there's one more problem, right? How about you guys start that one first by yourself, and then I'll catch up. So write your balanced equation first.
That's
Phosphoric acid is, phosphate has a 3- charge, so it's H3PO4.
What?
How about